Hello physics students, this is Dr. Brinzi here, and this is an example problem for lesson 2.6, which is talking about properties of properties of projectile motion. So we have a baseball here that is hit with an initial speed of 70 meters per second at an angle of 50 degrees above the horizontal. And I'm being asked three different questions. First of all, how long does it take the ball to reach its maximum height? Then I'm being asked, how high does the ball travel? Then I'm being asked, how far does the ball go horizontally when it reaches its maximum height? So, one way to begin is actually complete a diagram, and I actually already drew a parabola here. And this is the point that I'm interested in. And then I'm given some information about the initial velocity. So let's draw that initial velocity. So it tells me that the ball was hit at 70 meters per second at an angle of 50 degrees with respect to horizontal. So let's go ahead and set up our givens here. X and Y, and write down our usual givens. Alright, and let's see what we have already provided to us. Do we know anything about the X? Now, before we immediately say no, I need to tell you what we're interested in for this particular problem is not where the ball lands, but actually we're interested in the apex. In other words, its highest point. So this is where we're interested in finding X and Y. We don't know what those are, but we are interested in them because part C asks for how far did the ball travel horizontally. So that will be its X position. And then part B asks how high does the ball travel, so that will be the Y position at this point. So, take careful note that what we're interested in is this apex, and we're not going to even bother worrying about this entire half of the parabola. So, consider this like our finishing position here, even though we know the ball is going to continue. But that's the point of interest where we want to look at. We don't know anything about X yet, so we do want to find out about it, however, so let's go ahead and put a question mark there. We're starting off at an initial position in X. We'll assume that's the origin, so we'll say that's 0. Do we know anything about the velocity of the ball when it's at its apex? No, we don't right now, so we will leave that blank because we're not interested in it either. Do we know anything about the initial velocity in the X direction? Now be very careful here because it's very tempting to put in 70 meters per second here, but that's not correct because this is not being launched horizontally. This is being launched at an angle. It's being launched at an angle, so we actually have to break this down into X and Y components. You can think of it as being made of an X vector and a Y vector like this. So the X vector is the one in orange. Its length is Vxi. That's what I'm interested in. And how do I find out this if I know the angle and I know the hypotenuse? Well, that function, that trig function, is going to be cosine. So to find Vxi, I have to take the hypotenuse and multiply that times cosine of the angle. And when I do that, whoops, sorry about that. It turns out that the Y initial velocity is going to be sine of 50 degrees times our hypotenuse. So that's why I've written 70 times sine 50 degrees for my initial velocity in the Y direction. Alright, I think my next step here, I evaluate this, and that turns out to be 45.0 meters per second, so I'm going to go ahead and fill that in there. I'll come back to evaluating this in a moment, but let's finish off the X column and then work our way down the Y column. We know that there's no acceleration in the x direction because gravity only acts vertically, so a sub x equals 0. And let's turn our attention to the y column. At our finishing point up here, we don't know how high this is above ground, so we don't know its y position, but we are interested in it, so let's put a question mark there. Do we know anything about our initial position? Well, it starts off here, and we called this the origin, so that y position is 0, the initial y position. Do I know anything about the y velocity when it reaches its maximum height? Now, it's not given to me in the problem, but this is where it's really important to understand your properties of projectile motion, because we learned in our in-class notes today that there is no y velocity when the projectile reaches its peak. We looked at the x velocities and we noticed that they were all constant, so this thing will have an x velocity, but it's not going to be moving up or down when it's at its highest point. Up until this point, it's been going up in the upward direction, but here it turns around, and the moment it turns around, remember, its instantaneous velocity in the y direction has to be 0. So our initial y component of velocity is 0. Not because it was given to us, but because we know the properties of projectile motion, and at its highest point, Vx equals, or excuse me, Vy equals 0. Do we know anything about the initial velocity in the y direction? Yes, we do. We took a look at this triangle right here, and we wrote down 70 times sine of 50 degrees. When you evaluate that, that becomes 53.6, so we can plug 53.6 right there. Do I know anything about my acceleration in the y direction? Yes, it's due to gravity, and gravity is always acting 9.8 meters per second squared in the downward direction, so AY is negative 9.8. Okay, it looks like I have all of my givens except time. Let's see. I don't know what the time is. I don't know how long it took for the ball to get up to here. But I am interested in finding that out. That's the first thing I want to find out. So let's put a question mark there. Alright, now my given table is filled in as I can possibly make it right now. Let's go ahead and actually identify our equations. So these are the 5 equations that we can use. And there we go. Now let's go ahead and figure out which ones we can eliminate because we're not interested and we don't know a particular value in that equation. We don't know and don't care about Vx, which is the velocity in the x direction. The only equation that contains that is this one right here, so let's cross that out. All the other variables I'm either interested in or I know, so this is the only equation I can eliminate. Well, darn it. I mean, when we were doing problems before, we ended up with just 2 equations, but here we end up with 4. So if you run into this case, it's always a good idea to figure out what the time is first. And you want to figure out the time in the easiest way. So let's figure out which equations contain time. So we have this one, we have that one, and we have this one. Now, if I want to use this one, I have to know the other 3 variables in the equation. I do know that, that's 45. I do know this, that's 0, but I don't know x yet. So I have to hold on to this equation. I can't use it just yet. Let's take a look here. Well, already I see here that I have a y, and y is one of the things I want to know. I haven't found it out yet. So already I can tell you that this is not the equation that I want to use. let's take a look at this one. This is the last one we have left. Do I know Vy? Yes, I do. We figured out that that's 0. Vyi, 53.6, yep. Ay, negative 9.8, yep. So I can fill in the other 3 variables for this equation to solve for time. So let's do that. I'm going to have to do that on another slide here, but everything that you've written down here is what I'm going to put on the next screen. So don't worry about frantically drawing, writing what I have to write here. Just going to give my my program here an opportunity to write all that stuff down we wrote on the last slide. And getting close, getting close, getting close. Now the equations. Equations. And we're getting there. Almost there. And we just have to cross out that one. Okay, so we said we're going to use this equation. So let's go ahead and do that. I'm going to rewrite it down here. And then plug in the values that I'm given. Okay, and if I solve this for t, I'm going to subtract 53.6 from both sides, then divide by negative 9.8. I'm sure you know how to do that, and we're going to end up with a time of 5.47 seconds. Okay, so that's the answer to part A. So I can go ahead and write that as my answer for part A, and I can also put it in the givens chart over here, because now I know what that is. Okay, so with that knocked out of the way, I can figure out x or I can figure out y. Well, the problem asks me to figure out the height first. It says how high will the ball travel, so in part B. So let's figure out y first, or y next actually. So let's write the equation that will help us figure out y. Well, it turns out it's going to be this equation right here. You could use this equation right here. There would be nothing wrong with using this one here. I'm just going to go ahead and use this one because we're more used to using this one than the one down there at the bottom. So I'm going to go ahead and rewrite that equation to remind us what we're using, and then I'm going to go ahead and plug in some values. Okay, so these are the things that were given to me or that we just figured out. And if I evaluate this thing right here, I'm going to get some number that's close to 293. And then if I evaluate this thing, it turns out it's going to be negative 146.6. So if I take the difference between those two, it turns out that y equals 146.6, or I'm going to round it up to 147 meters. So this is telling me that the ball, when it's at its maximum height, is at a height of 147 meters above ground. Okay, so that answers part B. So part C says, how far has the ball gone horizontally when it reaches its maximum height? Well, that's where I have to figure out what x is. I'm going to give myself a little box down here in the bottom right. I just have just enough space. And let's rewrite the equation that will give me x. And plug in the values that I know. I know that xi is 0 and vxi is 45.0. And it turns out when I evaluate this, I'm going to get a horizontal distance of 246 meters. So when the ball reaches its maximum height, the horizontal distance it will be away from the launcher or from the bat is going to be 246 meters. So to get to the ball, I have to go 246 meters in x horizontally, and then I have to go up 147 meters to get to the ball itself. And that's how you deal with problems that involve knowing properties of motion, of projectile motion. And we couldn't have done it. It would have been impossible for us to do if we didn't recognize that at the very peak, when the ball is at its maximum height, that the y component of its velocity has to be equal to 0. Because it was going up, it's going to turn around at that very instant and start going down. And we know that when something turns around, its velocity in that direction has to be 0. Okay, so that's an example problem of properties of projectile motion. I hope this video is educational, and I look forward to seeing you soon. Bye.